Hi folks, this video tutorial belongs to the playlist which is intended for people who are either new to the 3D Experiences FEA solver or are transitioning from the Abacus CAE program to the 3D Experience release 2022x. I want to remind you that the FEA solver in 3D Experience is actually the Abacus program. The way the tutorial works is that I have selected a whole bunch of video tutorials from YouTube where problems are done in a step-by-step way by other YouTubers using the Abacus CAE program. So I try to show you in a systematic way how to retrace the steps that they have done in 3D Experience to solve the same problem. Now, the problem that I'm going to be doing is a dog bone like that. So this is a part that has a thickness of 1 millimeter, and its stress strain curve is the engineering stress engineering strain curve is given according to following data. Young's modulus and Poisson ratio are up there, and the ends are subjected to a load of 2000 megapascal from both sides. What we like to do, and this problem is done by this professor here at the University of Alberta, Dr. Petit, and here is the reference. So he has selected these dimensions and solved the same problem with plain stress element because the thickness is small, and it's a fairly good assumption that this is a plane stress problem. Now, uh, of course, because of the symmetry, he is modeling only 1/4 of this geometry. And there is a stress pattern here. The end is subjected to that load, and you get a 1 meter stress distribution like that, and it doesn't actually complete the job. The job terminates at some point, but you're going to see what that entails. Now, in 3D Experience, we do not have the plane stress or plane strain elements. Therefore, what we do to replicate that, I can either use solid elements to solve that problem, or I can use shell elements, which flat shell element, which are being pulled from both sides. Essentially, it's a membrane element, and it replicates the plane stress condition very well. Now, uh, in this tutorial of that professor, he shows you how to start with the engineering stress, engineering strain data, and convert it to the true stress and plastic strain data. So I'm not going to go through the process, but this is fairly well established. You start with strain, engineering stress through a bunch of formulas, which are basically here. You come up with this data that goes into the 3D Experience program. Now, here is my Excel spreadsheet. So I have taken these things and put it in an Excel spreadsheet myself, and I'm going to import this instead of typing this thing one by one. I'm going to import it into the 3D Experience. Now, the result that he's getting is a stress versus time. Now, this is a dummy time, so it's basically it's percentage of the the amount of load that is incremented applied, and I told you that it's going to abort after a while, and you'll see why. Abort after a while, it doesn't go all the way to 1, time being 1, the dummy time being 1. It aborts at some point. You'll see why. This is under load control, and we come back and do it under under displacement control, okay? Which we're going to get a curve like that, and you will see that this is the elastic region, this is the plastic region, and at this point where this is the last stress point, basically the program assumes that the stress is constant, and you'll see what's going on. All right, so let's go ahead here, because we are dealing with shell element. I'm going to start with generative shape design. There we are. Okay, in view of the fact that we are modeling this plate with shell elements, uh, I need to create a surface, and that's why I'm in the generative shape design. So regardless of how you do it, you have to create a geometry like that, and then of course put a surface through it. So here's my approach to the problem. On that vertical plane, I will sketch a profile, bunch of broken lines. We'll dimension it in just a minute. That, all right. And let me also draw a line here, a horizontal line. Okay, very good. So let's dimension. This is 225. That guy is 75. I'm using the same dimension that is used in that reference that I showed you. This is 50, and this is also 50. Okay. Now we're going to have to draw a circle here. Let's say an arc. This thing up here. Okay. And we want this and that. So I have to basically make this point coincident with that point and this circle to go tangent in a tangent way to that line. So there are different ways of doing it. So here's the way I'm going to do that. I select this point here, control that point, and then down here in these constraints, there is constraint defined in the dialog box. I'm going to say coincident. Okay, and then I want this curve to be tangent to that curve, to that line. So this curve control that line, and once again in the same place, I can specify tangency. There, that does it. Okay, so this is all done as far as the sketch is concerned. We exit, and now we have to put a surface through this thing. So you look at because we're in the generative shape design, surfaces can be created here. There is a tab here, surface, and there's one that says fill. So if you have a closed path, you can fit a surface through it. So fill it with a surface. So select this, nothing complicated. There's my surface. Let's look at this thing from the front because this is essentially a two-dimensional problem. So there's no reason to look at it in 3D. So let's look at the front view, right? These are the different orientations. Okay, now why don't we create our materials? So we go to tools, create a material. Let me call this thing this is dog bone sample, May 7, 2022. Okay, so okay. So a shell is going to be created, and I have to use that empty shell and basically apply it. Right, dog bone sample, May 7. Right click, apply. You're done with this. I'm going to close it, and I'm going to apply it to that part. Okay, good. So now we can go and fill in the results, the values. Okay, so under structures, abacus multiphysics, mechanical, elasticity, elastic, and the Young's modulus is 200 gigapascal or 200,000 MPa. Poisson ratio is 0.3. Okay, good. Then we go to plasticity. because remember, what we need to do is to put this table into it, which is the true stress in MPa versus plastic strain, okay? The calculation is done. This table that's going to go into 3D experience. So let's go back here. So plasticity, metal plasticity, plastic. Yeah. So here's a table that you have to input. You can do it line by line, or entry by entry, or you can import it. Now, in the CAE, Abacus CAE, there is a possibility of going to that spreadsheet, Excel spreadsheet, copy those columns and comment down and do a paste here, control, what's that, control V. It doesn't work there. So there's something that particular feature doesn't work here. So I'm going to go import. I have created already a folder here. Okay, there. This is that Excel spreadsheet that I showed you. So you say okay. So there we are. So what you see there is precisely this information. Okay. So that's pretty much it. So we say okay. It's isotropic hard running, so that was the default taken. Now we're going to go mesh testing. So we go to uh, structural model creation. Basically, that's where the meshing is done, things like that. There we are. You select an empty FEM. You have to mesh that yourself because surface. Okay. Now, let's mesh this thing first. So we go to meshing tab. There's a meshing tab. You're going to take a nice surface quad mesh. And I think in that reference, the professor is taking a linear, bilinear elements, so first order basically. So I'm going to do the same thing. There's the first order one. You select that. Let's put down 4 millimeters here and see how it looks like. And you say mesh. Yeah, that looks reasonable. You say okay. Now the other thing is that we have to specify the thickness of this part. So we go to properties. There is your shell thickness. Click on it. You select you can select the surface either from here, see that either from here or from the screen. Okay. So selection, support, selection, and then we're going to select the fill, and then we have to put a thickness here of 1 millimeter because the thickness of the sample is 1 millimeter. And that does it. So now we're going to go and apply our restraints and things like that. So we go to structure scenario creation. Don't forget to save regularly in case you lose connection, the computer crashes, etc. Now we're going to select a model that we created, find a model that we created. Good. So under the procedures, you want to do a static analysis right here, static analysis, and let us put a initial time increment of 0.01 and the maximum time increment of, I'll put down 0.1. These are probably excessive, but that's okay. And notice that under the advanced, the NLGeom button is on, nonlinear geometric effect is on. That's fine. All right. Let's apply our restraints. So we go to restraints. Uh, this edge, see this edge? This edge is a plane of symmetry. So let's go to fixed displacement. And I'm going to try to select this, but it doesn't work. It doesn't let me select it. So that being the case, there's a few things that I can do. For example, something is blocking that selection. So let's go ahead and see what it is that's blocking. Say cancel. let's actually do the following. So under right click under visibility manager, let's say show me the part. Okay, here is where you control things that are blocking your view. And I mean, if you don't want to see the mesh, all you do is say don't show me the mesh. There we are. Okay, so let's try it now. Fix displacement. Okay, you see this sketch is big, so let me hide the sketch, and now I should be able to select this. How about hide the, let's try hide the fill. The problem is that hiding the fill is not going to do you any good. Okay, so let's see now. Uh, oh, there we are. I did select it. Okay, I did eventually select it because as I was moving the cursor a little bit above it, it will take the entire surface, but I don't want this bottom edge. Now, this is a plane of symmetry, and if you look at it, coordinate system here, uh, that okay, that line does not move in the direction Z. Obviously, nothing comes out of plane, direction X, and rotations are exactly the opposite. So if this is free, this is fixed. These are selected, these are fixed, these are free. That's the symmetry boundary condition with shells. So we say okay, and do exactly the same thing on this other side. So let's do another fixed displacement. Try to select this edge right there. This does not move in the direction Y, and obviously nothing moves in the direction X perpendicular to the screen. Rotations are opposite. If this is free, this is fixed. Good. We now want to move this. Sorry, we want to apply in our first loading condition, load control, right there. We want to apply a load of 2000 MPa to that edge. Okay. So this is kind of weird because if you go to loads, and if you check the force, if you check the force, there is something that says shell edge load. Because you're applying a force to shells, you have to use this, shell edge load. Okay, now, you select that edge, okay? Now, first of all, this unit, this should be, when you apply forces to edges of a shell, it's usually specified in the form of Newton per, I don't know, Newton per millimeter, okay, or Newton per length, okay? So what we're going to do is we are going to take this number, 2000, multiplied by the thickness. By the thickness is 1. So it's going to be 2000 Newton per millimeter, okay? 2000 Newton per millimeter. So what we're going to do is go there and type, first of all, negative 2000 Newton per millimeter, and it's going to convert it to that unit that you saw there, right there. I could not figure out where you can change this weird unit, okay? But this is correct, except that I typed 2000 Newton per millimeter, and it automatically converted to what was default in the preferences. So not good. I couldn't find it. Okay, good. That's pretty much it. So first of all, let's save. This is going to run, but it will not go all the way. It will bomb out. It will not converge at certain stage, and it will bomb out. However, that's not a total loss because we can look at the results up until that point, the previous basically increment. So that's okay. Why don't we wait for the save to take place? This is real time, as you can see. I'm not going to do any cutting unless it becomes excessive, so I may cut the video, but I haven't done that yet. Okay, 90%. Saving operation. Okay. Okay, good. So we go to simulate. Let's do first a model check. There is something I forgot to show you. Let's check something. You see here, you see here, right there, element type. See this? Let me click on it. Notice that the type of elements is selected here. This is full integration. These are full integration. But if you want reduced integration, you can use reducer. In that in that reference, they are full integration. Okay, so I want to keep it like this. Good. Okay, let's go do a simulation check. This is something that I was going to show you earlier, but I forgot. So got a digression basically. So now we're going to do the simulation check, see if anything major, obvious is missing. It's not going to do. Okay, so let's run it. This is simulation check, not running yet. This problem could also have been done with solid elements, and it's fairly straightforward there. Okay, it's almost finished. Okay, good. And now we're going to simulate, which means we're going to run. Okay, let's run. So there's two things that we're going to do. First of all, we're going to check the at the last stage that it actually converges. We're going to check our stress pattern and check the numbers, see if they make sense or not. And then we're going to try to generate a curve like that at a particular location. As the load is increased, we're going to find out what is the 1 meter stress at a particular node as a function of time. This is not real time, it's a dummy time, okay? Well, that's the percentage of application of the load, basically. So let's see. Check the iteration. It will tell you this is equivalent of the monitor in the Abacus CAE program. So it basically gives you different iteration, what happens to it. So it is converging, but there reaches a point around probably very close now that will bomb out. Okay, let's see. See, there is unsuccessful stuff begin to show up, iteration, and at some point, the increment becomes so small that it actually bombs out. There was a minimum. Remember, there was a minimum of 1 × 10⁻⁵ uh, 5 second, uh, dummy seconds per time. Now notice that this failed due to error. That does not mean that we cannot look at the results prior to that though. Okay, so it stopped. You say, okay, now, if I go, don't notice that it doesn't automatically give you the plus and things like that. If you want to do that, you have to go to the results yourself, and it's going to give you a warning saying that, hey, I did not converge. I did not finish the job all the way. The simulation was terminated before it could complete. Partial results may be available for the following analysis case. Okay, good. So notice that what happened. Let me move this thing out of the way. Or maybe I move this thing out of the way, make it smaller. All right, so this was the initial step, no load applied. Now, as you scroll down, you go to the last step. This is the last step. There is the stress distribution, which I don't particularly like because, let me see for a second. Uh, that's okay, actually, static step. So, yeah, okay, so let's check this against that plot. The numbers actually are not very far off. Like this one says 900 and, I mean, this red stuff is 937 uh, mega megapascal. Okay, so here, if you put the, if you put the cursor on this, this is around 800, 860, 870. So it did bomb out. However, and these are, of course, these are totally meaningless because there's zero essentially. So let's do the following. Let's do uh, a different run. So let me see. Oh, there it is. Okay, this last one. Forget about this last one. Take the one before that. Okay. So this, if you put the cursor here, it's around 850, 870, etc. So obviously we don't have the same mesh, and it doesn't bother me. So because it is kind of this pattern, and the numbers are not far off, 10, less than 10%, 5%. Now, if you want to see the mesh incidentally, you double click on this thing. You go to this tab here. You see that? This dialog box opens up. You go to this tab, say, show me also the mesh. If you want to see it, and say apply. There we are. Now, what I want to do is, so what this thing means, notice that it stopped at roughly 0.27. 0.27 time of 0.27. That means you did not apply the full load of 2000 MPa. Okay, it's uh, 0.27 of that was applied, and after that it did not converge. The solution did not converge, it stopped. Up to that point, at every increment, the solution converged. But at this point, it does not converge. Okay, you cannot increase the load beyond roughly 0.27, 0.26, 0.26 times 2000 megapascal. Okay, now let's do something else. Let us actually go ahead and plot the stress at this location, say 1 meter stress. This is all uniaxial pretty much, so 1 meter stress as a function of time, and the strain at this location as a function of time. Can we do that? The answer is yes. You go to plots, you go to, what is that, right there, XY plot from field. This pops up. Okay, so what do we want? Let's say that we want stress component, 1 Mises. Okay, that's good, 1 Mises. Select the point. So I'm going to select this point. See, I'm putting the cursor there. And so see, it picked point number 1. If you don't want to know what the coordinates of that point are, incidentally, it is right here, 0, 0. If you want to delete it, you want to change it, etc., that's fine. But this is fine with me. So I want the plot of that point, stress at that point, 1 meter stress at that point as a function of basically time. And let's say apply. There. This graph is that graph that was generated in the video tutorial on Abacus CAE. We also want the axial strain. So if you go here, now we're going to switch this. Instead of variable stress, let's go to, for example, right here, plastic strain component, which component is it? W22 in this direction. And it says deactivate the existing plot. No, let's not deactivate the existing plot. I uncheck that and then say apply. So this is the equivalent of that. Okay, good. So close that. So far, so good. We're getting very similar results. So close that, and I'm going to close this. Okay, so now we're going to go back to scenario. This time, we're going to delete the load, and we're going to pull this thing by a certain amount. So let's see now. The load is here. Edge load. I'm going to delete this. We can also deactivate it, but I deleted it. So let's go to the load tab here, and there's the load tab. Under translation, this edge in the direction Y, 50 millimeters. Okay, you will notice that this time it will complete the analysis, but we're going to come back and talk about it in a minute, okay? See that? Repeat the analysis using displacement control, 50 millimeter to the right. Okay, good. So there's no reason to go ahead and do a model check and simulation check. I always encourage you to do that, but I'm going to run it. This time it will go all the way to the end, but you'll see what goes on. So basically, it passes that point where it actually bombed out, but it'll give, generate garbage for you, and for a good reason. You see why. 50 millimeters. Remember, that's a lot of deflection. I mean, the whole sample was almost 450. I think it was 450 millimeters. This is 50 millimeter to the right. That's a gigantic uh, displacement. So it's going through. It passed that percentage that it stopped before. It was 0.26. Remember? Go ahead. You can also look at the plot view. So up until this point, maybe something was okay, or 0.26, and then it's working, but it's kind of garbage. You'll see that. You'll see. Duration. When it reaches one, it's all done. It's almost done. Actually, it's finished extracting the results. Okay, good. So let me close this. Notice that it did go all the way to the end. This is the last step right there. Okay, this is the last step. If you look at the displacement, let's check the displacement. It did go all the way to 50 millimeter. If you look at the 1 meter stress, these elements are so distorted that whatever you do is garbage here. But that is not the issue. If you go to that plot that you generated right here, see that? Let's go to that XY plot that you generated. It was history plot right there. This last one. Let me say, show it to me. Apply. Okay. Uh, Let me see now. What is this? Is actually this one is not the stress. This is the strain. So let me do the other one. Let's see. How about this one? Cancel that. How about this one? Let me see if this is a stress. If not, I'm going to do it again. Oh yeah, 1 meter stress. Apply. Right there. This is the strain. It kept it. That's fine. This, you see that? This stress versus time all the way to the end is that curve, which is this curve. The reason what happened is that we are making predictions. We are making simulation beyond the data that we gave it. Remember, the data that we gave 3D experience was like this. It stopped at roughly 937. It stopped there. We just said, I'm not going to give you any plot after that. I'm not going to give you any data after that. So what the 3D experience does, or Abacus does, it just draws a flat line after that. So it's calculating based on that flat line, fully plastic analysis, basically, which is, with no hardening, strain hardening, etc. So that is why when you apply low displacement control, there is no issue with convergence. It converges at every increment. It's just that it generates garbage. Up to this point, I gave it data. Then this is essentially a horizontal line. Now, I may have to change the mesh in order to get exactly what this fellow is getting. But anyway, I think you get the picture. So I hope this was useful, and good luck.